Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to cover the topic of parametric equations, what are known as parametric equations, okay? This section throws people for a loop sometimes because it's something you've generally never heard of until you get over in Calculus 2. You kind of wonder why it's taught at all. The dirty little secret is you don't use it that much, but whenever a system or something that you're studying in real life in engineering or in physics has a need for a parametric form of the equations, it's really powerful and it's really simple. You don't use them that much, but when you need them, you really need them bad, and it really helps your problem out a lot. So you cover it in calculus here. It has a fancy name, parametric equation. What does that mean? I think the easiest way to do it, rather than try to talk to you about it, is to show you. It's really not that hard at all, okay? Now recall, I'm going to recall some basic stuff that we all know. Recall that a curve can be represented by a function, okay? This is super basic stuff. There's no trick questions here. Here's a function, right? So what we have here in general is we have y, which is also called f of x, okay? And what we do, and I'm going to write down some simple stuff here, is we take and we plug in x into this function, which is just some equation or whatever. And what we do is we get something called y out. So we plug in something into this function, and we get y out, okay? And you all know, back from, algebra, that when you do this, you get 2 points. You get an x point and a y point, and you plot this thing on a graph. And this is at x comma y. You know this. This is sort of, at this point, this is like third grade math to you, right? You plug something in, you get something out. Okay. Now it turns out those are the types of functions that we've studied all of our math life up until now. And here we talk about the subject of parametric equations. It's just a different way to write a function, okay? Now, let me talk to you about something, and let me tell you something, okay? Let's say this function that you're trying to apply, it could be anything, but it goes like this, okay? Whatever, it's just some crazy looking function. And we say that this is the x coordinate and this is the y coordinate, okay? Now we have a function that we call f of x, right? That talks about the relation between x and y. We put a number x in, we get a number y out. That's exactly what we're saying here. Now it turns out that you can, and I'm just going to write it down in all its glory and then we'll talk about it. You can also write any function as a parametric function or a parametric equation, which is a big fancy word, and all it means is the following. Instead of having a single function that talks about the relationship between x and y, you can say that the variable x is a function of some other variable t, and y is a function of some variable t. Okay, so this is it. Okay, and I'll talk about why. T here is called the parameter, and that's why it's called parametric equations, because it's a parameter, okay? And it's called a parameter because this is a parametric equation. That's where the name comes from, okay? So what happens is t is now the independent variable. Okay, so way back in the beginning of algebra, you were always taught about the dependent and the independent variable. The independent variable was x, because that's what you varied, and the dependent variable, the variable that depended on him, was y, because that's what the function was written in terms of x, right? You plug in x, you get y. Okay, here, the easiest way to think about parametric equations is this. Instead of y depending on x, you split everything up. This curve is overlaid onto an xy grid, and I have an equation that only talks about the x points of this curve, and I say that they're related to t. Now for me personally, the easiest way I think of this, I always think of t as time. Okay, it just helps me. So think of t as time from now on. I think you'll be in good shape. X, the x variable, depends on time. Okay, y, completely independently of x, totally independently, these are not coupled together at all. This is a totally separate function. Y depends on time. Okay, so just back up to the 100,000 foot level for me and just think about this. If I start time at 0 and I have a function of t that governs the values of x, and of course I can calculate them because I know what the variable time is. It goes from 1 second to 2 seconds to 3 seconds to 4 seconds, whatever. At every value of time I can calculate the x value. And at the same time, I can calculate the corresponding y value. Okay, so at 1 second, 2 seconds, 3 seconds, 4 seconds, I calculate the y values. Okay, so at every value of time, I get an x value by plugging into this relation right here, and I get a y value at the exact same time. And that gives me x and y at the same time. And I can plot that on an equation just like I did before. So you see, it's really not that different from what you've already learned. Instead of having a function y in terms of x and plugging in x and getting y, here I've decoupled the coordinates, okay, and I have a function that only gives me the x's and a function that only gives me the y's. And it's in terms of time. As time marches on, I get values of x's and values of y's, and I pair them up just like I always have, and I plot them just like I always have. So for any function that's an x and y that has a function associated with it, I can define this parametric form of it that has the x coordinates in terms of some variable t that I like to call time, and I have the y's at that also at those values of t, which I call time. And that's why the books say that t is the independent variable. It's the variable that you have parameterized, sometimes is how they call it, okay? So what you have is, instead of one equation, you have two. So this section, what we're going to do now that we've introduced it is, we're not going to do too much. All we're going to do is we're going to look at some parametric equations and plot them. We're going to get a feeling for how they work. In the next sections, we're going to actually use them to do some problems like arc length and surface area and things that we've done before, but we're going to do them in parametric coordinates. So that's where we're going. But in this section, we're just going to simply look at some parametric equations and give you some practice with what they would actually look like, okay? So, in these problems, what we are going to do is two things. The first thing we're going to do is sketch the curve, okay? And the next thing we're going to do is we're going to eliminate, and I haven't even talked about this yet, but I will, eliminate the parameter t, okay, to find the Cartesian version. Okay, now I want to explain that last bullet a little bit more. Let's go down here. I told you that a parametric version of an equation is going to actually be two equations, one that talks about x and one that talks about y. Both of them are going to be tied to this common variable. I call it time. It could be any letter, but usually it's called t for time, okay? What you can do is, since you have an equation of x of t, and you have y of t, you could theoretically solve for t in one of these equations, plug it in the other one in terms of its t, and then you would have the equation in terms of only x and y. So in that case, what you've done is you've eliminated the t by solving one equation for t, plugging it into the other one. You now no longer have any more t's, okay? T is gone, and you have your function in terms of x and y, which are the types of functions you've always been dealing with. And that's how you go from one to the other, from parametric version back to a function, regular function version, and vice versa. So that's what we're going to do, and here's the first problem. What we have is x is equal to 1 minus t, okay, and y is equal to 2 plus 3t, okay. So this is a parametric form of some curve. We're going to plot it. That's what we're going to do. And you can see we have x as a function only of t and y as a function only of t. And all we're going to do is t is time. Think of it that way. So what we're going to do is we're going to plug in various values of t for time, okay, and we're going to get corresponding values of x and y, and we're going to plot those, okay. So we make a table, just like you were back in algebra. We're going to make a table to actually plot this thing. So we're going to have t, and we're going to have x is equal to 1 minus t, and then we're going to have y is equal to 2 plus 3t, okay? And we're going to actually plot this. Now I'm just going to pick some random values here, -2, -1, 0, 1, and 2. So this is time, and I have some negative time, some positive time, reference to 0 time, okay? Let's just go ahead and fill them in. Okay, so what we have is x, for x, it's going to be 1 minus t. So it's going to be 1 minus t, which was -2, and that's going to equal 1 minus a -2 is 1 plus 2, which is 3, okay? And then y is going to be 2 plus 3t. So it's going to be 2 plus 3 times t, which was -2, is 2 plus, this is going to be -6. So really what it's going to be is 2 minus 6, which is going to be -4. Okay, so I'm going to stop there for just a second and tell you. At this moment in time, at -2, okay, at this moment of time, the point on the graph that we will draw in a minute is going to be at 3, -4. So we have just defined an x value and a y value at this time. That's all we've done. That's all a parametric equation is, okay? Now let's look at the next time. It's going to be 1 minus -1, okay? So that's 1 plus 1 is 2, okay? And then over here, it's 2 plus 3 times -1, plugging in for here. And that's going to be 2 minus 3, which is -1. Okay, plugging in at 0, it's going to be 1 minus 0, which is 1. And over here, it's going to be 2 plus 3 times 0, which is going to be equal to 2. Okay, plugging in for 1, 1 minus 1, because we're plugging in for t, there, is going to be 0. And over here, it's 2 plus 3 times 1, 3 times 1, which is going to be 2 plus 3, which is 5. Okay, and then I have over here 1 minus 2, which is equal to -1. And over here I have 2 plus 3 times 2, 2 plus 6, which is 8. Okay, so I have a table of values and I can plot them. And all I've done is at every value of time, I have a corresponding x and y. So I have points, and I can plot those points, and you all know how to do that. So the next thing we're going to do is we're going to go ahead and graph this. Okay, let me go ahead and draw a nice big coordinate system here. Okay, something like this. And this is x, and this is y, just as it's always been. Nothing has changed, okay? Now, let's look at this first value that we have. The point is 3, -4, okay? So what I'm going to have is x is equal to 3, 1, 2, 3, and y is equal to -4, 1, 2, 3, 4. So I have a point right here, okay? That's the first point, okay? Now let's look at the next value of time, 2, -1, 1, 2, and -1 is right here. Okay. Next value of time is at 1, 2. So 1, 1, 2, which is right here. Okay. Next value of time is 0, 5. So I've got 1, 2, 3, 4, 5. 0, 5, which is right here. Okay. And the next value is at this one here, -1, 8. So -1, 1, 2, 3, 4, 5, 6, 7, 8. So that one's going to be right about here. Now, let's look at what it looks like. I think you can see it's basically going to be a line. Okay, it's going to be a line. Okay, so it goes through these points, which are right here along the line. Now, one thing you need to do when you draw these parametric equations like this, because you're marching kind of in time. You see, this is back in time, and this is going forward in time. That's what I like to call time. Then what you're going to need to do when you draw these things, this was the first point you plotted in time, and this is the next point, and the next point, and the next point. So what you usually do is you draw arrows, and what you're saying is that this curve goes. It kind of traces up from here to here if you were to be moving in time. So you kind of get a sense of the shape of the graph, and you also get a sense of what it's doing in terms of time. As the parameter t, which I call time, increases, the graph goes up like this. Okay, that's why the arrows are going up, because this is the first point that I plotted, the second, the third, the fourth. As time marches on, the plot goes up like this. Okay, now the next part of what we said we wanted to do is we wanted to eliminate the parameter t to find the Cartesian version. Okay, that's what we wanted to do next. Okay, so let's see what we get when we do that. Okay, the two parametric forms was x is equal to 1 minus t, and y is equal to 2 plus 3t. Okay, so what I'm going to do is I'm going to solve this one for t. This is like what I said I was going to do before. Solving for t, I'm going to have t is equal to 1 minus x. Okay, make sure you agree with that. Basically, you take this t, you move it over here. You take this x, you move it over here. So it's going to be 1 minus x. I'm going to take this t, and I'm going to plug it right back into the other equation. So what I'm going to get when I do that is I'm going to have y is equal to 2 plus 3t, but this is what I've defined to be t, 1 minus x. Okay, 1 minus x. So let's go ahead and continue to simplify. Y is equal to 2 plus, distributing this 3 in, 3 times 1 is 3, minus 3x right here, okay? And let's simplify here. Y is equal to -3x plus 5. This is the Cartesian version. Now, what does that look like to you? That's a line, obviously. Mx plus b, this is a line. It has a y-intercept of 5, okay, a y-intercept of 5. Let's look back here. Y-intercept's at 1, 2, 3, 4, 5. It has a slope of -3. The negative means it's slanting this way, which it is, and it's sloping at 3. So you can see right here, you go up 1, 2, 3 over -1, so you do have a slope of -3. Okay, so that's all this parametric equation stuff is, and we're going to do a few more problems and we're going to see that. You've got two equations, one equation that governs x and another equation that governs y. They're all in terms of a third parameter, that's why it's called parametric equation, and we call that time, at least I call it time, it helps me think about it. And when you're plotting these things, you're just marching along your parameter t, calculating x and y, plotting your points, and to eliminate them you're simply isolating t and plugging it into the other equation, and you're getting a relation in terms of x and y only, which is the types of functions you've been used to dealing with forever. Okay, now the next problem is going to be x is equal to 3t squared, and y is equal to 2 plus 5t. Those are my parametric equations, and t goes from 0 to 2. So in this case, the problem was actually given to us. It was actually given to us that t goes from 0 to 2. So that's what I'm bound by. So I'm going to go ahead and create a table just like I always do. And I'm going to have an x value, which is 3t squared. And I'm going to have a y value, which is 2 plus 5t. Okay? But now I know that t is limited and it's already defined for me. T goes from 0 to 1 to 2, okay, and all the values in between, obviously, but for the ones that I'm calculating here, I'm just going to do that. X is going to be 0, 3 times 0 squared. Y is going to be 2 plus 0, which is 2. Plugging in 1, I'm going to have 3 times 1 squared, which is 3. And for y, I'm going to have 2 plus 5 times 1, which is 7. 5 times 1 is 5, plus 1 is 7. Okay? And then here I'm going to have 3 times 2 squared, which is going to be 2 times 2 is 4, times 3 is 12. And here I'm going to have 2 plus 5 times 2. 5 times 2 is 10, plus 2 is 12. So I'm going to have 12 and 12. So what does this function that's governed by this parametric form of an equation actually look like? Let's go ahead and draw it. Okay? I have x and y, just like I always do. Okay? Now at 0, my point is 0, comma 2. So it's right there. At the next point in time, x is equal to 1, 2, 3, but y is equal to 7. 1, 2, 3, 4, 5, 6, 7. So 3, comma 7 is about right there. At the next point in time, 12 and 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's going to be 12, comma 12, right around here. So this function looks like it bends over. It starts here at 0, comma 2, and it goes up, and it actually bends. I kind of missed my point here, but it kind of bends over because that point's right there, and it just kind of goes on like this and bends over. Okay? So it's kind of one of these functions that bends over like this, and that's what it looks like. Now, how would you eliminate and find the Cartesian version of this by elimination? Well, you know what x is equal to, and you know what y is equal to, so it's a simple matter of solving for one and plugging into the other. So I'm going to pick x squared, and I'm going to go ahead and I'm going to solve for t. So if I know that my equations are x is equal to 3t squared and y is equal to 2 plus 5t, okay, I can solve for t squared, okay, which is going to be t squared is equal to x over 3. So then t is equal to square root of x over 3. Okay? T is equal to square root of x over 3. Okay? So I can take that and I can plug it in over here, which is going to be y is equal to 2 plus 5 times t, which is square root of x over 3. Okay? All right, so I'm just going to do a little bit more simplification. I'm going to take this 2 over to the left, and that's going to be 5 times the square root of x over 3. And just to get rid of the radical, I don't have to, but I'm just going to go ahead and square both sides. So it's going to be y minus 2 squared is equal to 5 times 5 is 25 times x over 3. Because I just squared the right-hand side. So I squared the left, I squared the right. 5 squared is 25, and then this is just going to have the radical gone. Okay, so I squared the left, and I got y minus 2 squared, and on the right I got 5 squared is 25, and I got rid of this radical by squaring them. And then the next thing I'm going to do is I'm just going to try to get x by himself. So I'm going to multiply over here, and I'm going to have 3 over 25 times y minus 2 squared is equal to x. All I did was I take this 3 and this 25, multiply by 3, divide by 25, and I have x over here. So this isn't perfect because usually your functions have y as a function of x, and here I've solved for x on one side, but it gets the point across. I've eliminated t, and I only have a function in terms of x and y only, so I've successfully eliminated. Basically, you solve for t, you plug it into the other guy, and you do as much simplification as you can just to eliminate that t, and that is the Cartesian version that they'll be asking you for in your problems. Okay, now the next problem is my parametric equation is going to be sine of theta. So when I plug in theta, I'm going to get x, and y is going to equal cosine of theta. Okay, and theta, we're going to say, is only going to be able to go from 0 to pi. Okay, now this is an example I brought up because most of the time when you see the parametric equations, they're in terms of t for time. Okay, here's in terms of theta. And the reason sometimes you see them in terms of theta is because usually you have something rotating. So if something's rotating, so at some angle theta, it's defining x and y of whatever you're looking at in terms of some angle theta instead of some time. So this theta, don't let it scare you. It's just the parameter. It's just that independent third parameter that usually we call time. It's something else that x and y are defined in terms of. Okay. So what is this thing going to look like? We make a table just like we always do. We're going to have theta, which is our parameter. Usually we call it time, but in this case we're calling it theta. And x is going to be equal to sine theta. And y is going to be equal to cosine theta. Okay, just like always. And we're going from 0 to pi, so I'm going to pick 0. I'm going to pick pi over 4. I'm going to pick pi over 2. I'm going to pick 3 pi over 4. And I'm going to pick pi. These are equally spaced angles along the unit circle. Pi over 4 at 45 degrees, pi over 2 up at 90, 3 pi over 4 over here, and pi right over here. So all I'm doing is I'm looking at a half circle in terms of theta and see what we have. Okay. Now for x, sine of 0 is 0. Okay, so that's the answer for x. For over here, cosine of 0 is equal to 1. Okay, so at this angle of 0, x and y are given right here. The next one, sine of pi over 4 is square root of 2 over 2. Should know that one. And the cosine is the same thing. Cosine of pi over 4 is square root of 2 over 2. Okay, now what's the sine of pi over 2? That's straight up and down pi over 2, so sine is equal to 1. And cosine of pi over 2 is cosine of here. There's no projection on the x-axis, so cosine of pi over 2 is 0. Okay? Now the sine of 3 pi over 4, okay? Remember, I'm looking at right here now. 3 pi over 4 is right over here. The sine is equal to, again, same thing, square root of 2 over 2. It's positive because you're over in this quadrant. And the cosine of 3 pi over 4 over here is going to be negative because cosine projection over here is negative. Negative square root of 2 over 2 from your trig, okay? And finally, sine of pi all the way over here, there's no projection on y, so it's 0. And the cosine of pi is negative 1 because it's also over here, okay? So that's how you fill that stuff out, and that's why you really have to be good at trig in calculus, because this kind of stuff you'll have to do it on your tests, and you won't be able to use a calculator to get this stuff. You'll have to know the fractional form of it, okay? So, what does this thing look like? That's our next question. What the heck would it look like, okay? So let's try to draw that here. Let's draw this right here. If this were x and this were y, what would it look like, okay? Now, at an angle of 0, which is what this angle is, theta, at an angle of 0, my x-coordinate was 0 right here, and my y-coordinate was 1. So at theta equals 0, I'm right up here. At theta is equal to pi over 4, I'm at square root of 2 over 2 and square root of 2 over 2. So right here is 45 degrees at pi over 4, okay? If you take square root of 2 over 2, it's about 0.7 in your calculator. So if this is 1, 0.7 is about right here, and 0.7 is about right here. So if you look in the middle, 0.7 is going to be right around there. Okay? 0.7 comma 0.7. Okay? Okay, now at the next value of the parameter, I'm at x is equal to 1, y is equal to 0, so I'm at this point here. At the next value of the angle, I'm at square root of 2 over 2, negative square root of 2 over 2. So if this is negative 1, 0.707, comma negative 0.707, about right here. And then finally, at the final value of the parameter, I'm at 0, comma negative 1, 0, comma negative 1. So what you have found, remember, the earliest value of the parameter, I was up here, and as I marched down the table toward pi, I went around this circle like this. So this is going to look like this. It's going to go through here, bounce down here, and it's going to be a half circle. And the arrows, you should always be drawing like this. Okay, so the arrows go like that. So that means at the earliest value of the parameter, you go down like this. Okay, so that's what the thing looks like. Now, how would you eliminate this guy right here? The two equations you know is x is equal to sine of theta and y is equal to cosine of theta. Now, how would you actually combine those things to get rid of the variable theta? Well, this is not one of those cases where you can substitute in. I mean, you can't isolate theta and substitute in without a bunch of ugliness, because the only way to get theta by itself is to take the arc sine of both sides, and that surely isn't going to be nice. This is one of those cases where it's a little bit of a trick. If you remember that identity, okay, sine squared of theta plus cosine squared of theta is equal to 1. That's a simple trigonometric identity. It's always true no matter what. Now look, sine is given by this and cosine is given by this. So if I square this, sine squared, and put it in here, I'm going to be having an x squared here plus cosine squared, but cosine is given by y, so it's y squared is equal to 1. Now look what you found. Just by using that trig identity, you found that x squared plus y squared is 1, which you should recognize as the equation of a circle with radius 1. That's exactly what it is. It's the equation of a circle with a radius 1. Okay? So, you know, that's the thing here with parametric equations. You have an independent parameter, you have an x, you have a y, and you're varying this parameter and calculating x and y independently, and that's why you do it. Now, what you might ask, why would I even ever use this stuff? Okay? Well, like I said, there are some systems that are very, very useful to use parametric equations. If you get into that field and you need to use it, your life's going to depend on this stuff, and then you might go off into another area of science or engineering where you never touch a parametric equation in your whole life, and you never miss it. Okay? Usually, a lot of times, these types of representation of functions are useful when you have rotating objects. Okay? Like for instance. And I'm not an expert in this, but basically, if you have a rolling bicycle tire, like if you have a bicycle tire you're rolling down the road this way, but if you look at a point here, the point goes down, and if you were to plot the value of this point as it rolls across the ground, it would look something like this. It would go something like this. As this point rolls around, it goes down, and then it goes here, and then it bounces back up, and it goes over and over. As this point rotates around, it would kind of trace out a motion like this as the tire rolls down the road. Okay, now you can plot this. Okay, in terms of a function f of x, sure you could define this, but notice these ugly cusps are here everywhere, and that isn't really good for functions. Okay, it turns out that if you study these types of motions, which mechanical engineering might do that, or lots of areas in engineering might do that, if you write this motion in terms of a parametric equation, in terms of the angle of the bicycle tire, kind of like this problem right here, where instead of defining y in terms of x, which is sort of the traditional way to do it, you're going to have this ugly looking function, you may be able to define x and y in terms of the angle of the tire, okay? And it might make a function that's much simpler to operate on. And that's the kind of problems it's useful for. So you usually have to have very specific types of systems that lend themselves to these kinds of problems and make them simpler. And when you get into those kinds of problems, you'll know it because you'll have to use a simplification. Otherwise, the math gets really crazy. But that was a section on parametric equations. They're not that difficult. And if you just look at them, make your table of your parameter, calculate x and y, you can plot them like any other function and see how they behave, and go on from there in the study of parametric equations.